Hi everyone, welcome to this video on the drag forces lesson. This is lesson 12 in the Forces and Space scheme of work. The exposition in this lesson is going to look quite similar to the one that happens in 2 lessons time on terminal velocity, but really the emphasis here is not on the whole picture, it's just on the drag forces themselves. So I think it's really helpful to introduce drag forces in this lesson and then bring that together into a broader picture later on. The other thing I would say is that as we've seen throughout this scheme of work, this lesson is really just another way of reinforcing the core concept, which in this case, well, really the 2 core concepts, Newton's first and second law, and showing how when there's unbalanced forces and a resultant force, we get this acceleration. When the forces are balanced, there's no change in motion. And really this is introducing one layer of complexity in that we've got balanced forces, but this time on a moving object. And lots of students will think balanced forces, object must be stationary. And this is going to be the first time really that they see balanced forces on a moving object, which therefore travels at a constant speed. So to introduce the idea of drag forces, I think it's helpful to start with something very concrete. Something they'll all be familiar with is riding a bike, let's say, or even running, but I'm going to use riding a bike, and that experience of feeling air resistance, kind of feeling the wind in their face. So what I'm going to do first is sketch. Maybe I'll sketch a bicycle like this. You could just draw this as a blob. But I'll sketch a person riding a bike like that. And what I'm going to do is imagine we're at the point where this cyclist is just setting off. So I'm going to put v is approximately equal to 0. Now, we're going to cover speed in the next lesson. It's a tricky one. I don't know where to put speed in this scheme of work. Maybe it should have gone before this. So if you wanted to teach the next lesson before this lesson, so they're familiar with the idea of meters per second and so on, you could. But anyway, I'm just going to do it here. So we've got a speed approximately equal to 0. And what we want to show our students is that if the speed is approximately equal to 0, well, the 2 forces that are acting, and we're only considering the force in the horizontal dimension right now, the 2 forces that are going to be acting, you're going to have a forward thrust force. I'm going to exaggerate the length of this arrow just to show the contrast with the drag force in this case. I'm going to call this the thrust. You could call it the driving force as well, that's fine. And what you want students to recognise is that in this case, when the speed is very low, this drag force is very low. So something like this. I'm just going to draw a really little arrow to show that the drag is low. And you might want to introduce this to students by saying, well, when you set off on a bike, you don't really feel the wind in your face. You know, you can't feel that air resistance pushing you back. And that's because the drag force is quite low. Now what we could do is take one direction as positive. So I'm going to take this direction as positive, as we've been doing in previous lessons. So let's take that as positive like this, because that's the direction the cyclist is moving. And we could put some numbers on here. So let's say I've got 100 newtons here, and the drag, I'm just going to say, is equal to 10 newtons. So it's quite small. So if I needed to calculate the resultant force, it's equal to, I'm going forward, again, I'm just modelling the physical thinking process. So I'm going to say, well, this is in the same direction as positive, so that's going to be plus 100. That's in the opposite direction, so it's going to be a minus 10. And 100 minus 10, I just get 90 newtons. So I've got a resultant force in that direction. And it's quite a big one. It's quite a big resultant force. So that means this cyclist is going to accelerate really fast. And accelerate, as we've been saying throughout this scheme of work, accelerate means speed up, it gets faster. So let's say 10 seconds later, now instead of being approximately 0, now my velocity has increased quite a bit. Let's say my velocity has gone up to 5 meters per second. So I'm going to draw my cyclist again. Maybe I'll draw them having moved a bit. So cyclist. Now, this time, I'm going to draw the forces again. I'm going to start in the middle. I'm going to draw the thrust force, and you could elicit this by questioning students, or you could just tell them, but we're going to assume that the thrust force stays the same. So the amount of force that can be applied by the cyclist's legs just stays constant. So I'm going to put thrust equals 100 newtons. And then I'd probably ask students to think for themselves. I'd probably do a thumbs up, thumbs down, so I can check for the whole class's response. I'd say, well, what do you think's happened to the drag? If you're now going faster, is the drag going to be bigger? Is it going to be smaller? Or is it going to be the same? And hopefully they will recognise that the faster you go, the more wind, so air resistance is an example of a drag force, the more wind is kind of pushing into your face, and therefore the drag has increased. So now I'm going to draw a slightly longer arrow than I did before. Let's draw maybe like that. And let's say the drag is now 70 newtons. So if I'm calculating the resultant force again, I'm just going to abbreviate that to RF. Well, I'm still going to take that direction as positive because the cyclist is still moving in that direction. So I'm going to say it's plus 100 newtons. That's in the opposite direction, so it's going to be minus 70 newtons. Well, now I get, really put pluses here, shouldn't I? It's plus 30 newtons, so it's in that direction. But what you want students to notice is that because the drag force has increased, the resultant force has decreased. Now, here's a misconception that they might have. They might think, well, because the drag's bigger, now the cyclist must be slowing down. You still want to emphasize there's still a resultant force in that direction, but it's less than it was before. So the cyclist is still accelerating, but not as rapidly as it was before. I'll put accelerating less rapidly to try and keep it succinct. So accelerating less rapidly. And then you want to get to the final point. I'm just going to move this down a little bit. You want to get to the final point. So let's say another 10 seconds later, here we went from 0 to 5. Here, and you can make sure students are clear on this, we're going to go, because we're accelerating less rapidly, let's say we've just gone from 5 to 7. V equals 7 meters per second. So let's say the cyclist has moved further again. I'll put them over here. I'm going to draw the forces. Now what you can say is at this point, thrust is still going to be the same as it was, 100 newtons, because the cyclist is still generating the same force. That's what we're going to assume. But in this case, now, let's say the drag has got up to 100 newtons. I need to make sure those arrows are similar length. Maybe I'll make that a bit longer. So now the drag is 100 newtons. Now this is where you can really test students out, because the classic mistake to make here would be to say, the forces are balanced now. Sorry, I should have put thrust equals. The forces are balanced now. That means the cyclist must have stopped. But draw their attention back and say, hang on, let's think about the story. We started by accelerating rapidly up to 5 meters per second. We said we were still accelerating because there was still a resultant force, just not as rapidly as before. Now we're at 7 seconds. We can't just stop. That would be v equals 0. And what we want to do is elicit the idea that actually, if the resultant force is 0, then the cyclist is travelling at a constant speed. So we could do this calculation if we want to. It's just going to be plus 100 for the thrust, minus 100 for the drag. So that equals 0 newtons. So what that means is there's 0 resultant force, and therefore this thing is just travelling at a constant speed. And this is really, really important. What we'll see in the examples later on in this lesson is, because we're not going to go into kind of F equals ma calculations because it's only year 8, what we're going to see is lots and lots of examples where objects are travelling at constant speed and students have to work out the drag. And what they need to realise is that if a moving object is travelling at constant speed, that's because the forward force, whatever it is, it might be weight pulling a parachutist down, it might be thrust pushing a car or a swimmer or a a cyclist along forwards, whatever the forward force is, that's going to be balanced by the backwards force. And again, what we see here is it's just another application of the core concept. So that's how I would explain this. Then when we do the check for understanding questions, really the key things that I'm looking for are, do they get this point about Newton's first law? And then the other point to notice is, and maybe I didn't emphasize this enough just now, is what happens to the drag. As the speed increases, the drag increases. And that's a really, really important point that's going to unlock their deeper scientific thinking when we get to explaining what's going on in questions about terminal velocity. So we'll do speed equals distance over time in the next video, and then we'll come to terminal velocity after.